And with that, I'll pass things over to Dr. Derek Loftis. He is an assistant professor at the Virginia Institute of Marine Science and leads our water level work here in Virginia. He's been doing a lot of great work here and around the area, so I'll let him take it from here and share more about what's happening with his work in Virginia.
Great. Thank you very much for that introduction. I really appreciate it, Tina. So I've had the privilege of working on this project that's really focusing on flood monitoring and flood model validation using next generation water level sensors and community science data. Now these are essentially just some of the tools in the arsenal of a person that handles flood prediction. And so, of course, the goal with this is to improve the forecasts that are being provided for inundation prediction systems. In this case, most of the models we'll be talking about today are storm tide models capable of predicting storm surge and tidal flooding and a combination of both. But the ultimate goal is to fully incorporate rainfall-induced inundation as well through compound flooding when it pairs up with storm tide. So these types of things are really at the precipice of the modern research approach that we're looking at and working to embody in this endeavor. So the overview of my talk is going to first kind of introduce sensors and a platform of water level sensors in the Tidewater region of Virginia called StormSense. Next, I'll be talking about some next generation water observing technologies, leveraging machine learning and artificial intelligence through live webcam sensors as a new type of passive remote sensing technology we've been working to develop in collaboration with the U.S. Geological Survey. And then a third step for this is going to be introducing how we actually do storm tide forecasting and specifically also how we handle tidal forecasting. Then we'll delve into automated alerts connected to these water level sensors as one of the key resources that a lot of communities that are partnering with the whole instrumentation proliferation approach that's used with the StormSense project and others. Our goal is to provide some automated flood alerts that provide some credits to the individual communities that are attempting to be more resilient in these efforts. That provides some kickbacks to them through the community rating system through the National Flood Insurance Program. So automated alerts are important. And then, but also what types of filtering are involved so that you don't send erroneous flood alerts because that ultimately provides less intrinsic connection to the system for individuals that are involved because they're less willing to trust future flood alerts. And so our goal is to kind of make sure that we are streamlining the data that are available through application programming interfaces and then featuring flood validation of models that are driven by these sensor data. A lot of the work that we published previously has been available in the Marine Technology Society Journal that's been looking at the intergovernmental blueprint for community resiliency. And so just kind of as a pictorial outline of what I'll be covering today, I'm the lead for the StormSense project. It's won several awards related to flood prediction driven by sensors. And so real-time observation data provide us additional context to what's happening. We've got over 65 water level sensor locations at this point, and we are incorporating data from NOAA and the U.S. Geological Survey on the federal level, along with state data from the Department of Emergency Management in Virginia. We try to transparently share these data. They're geocoded using geographic information systems. The open API links or application programming interfaces mean people can ingest these data into their systems for actionable emergency management decision making, but also for community planning purposes in the context of sea level rise. They're also able to look at the data from past events and incorporate that into future community planning. And so the reason why this is important is mostly because if you look at the highest astronomical tides of today, that can kind of give you a very brief glimpse into what you would expect to be the mean tide level 20 to 50 years from now, depending on which projections you're looking at for actionable decision making. And so with that, we have 65 water level sensors that are tide gauges within the tidal region of Virginia. There are even more water level sensors in the riverine environments beyond the fall lines of the James River, the York River, the Rappahannock, and Potomac rivers as the major tributaries of Virginia. You can interactively access these data at the web link below. The collaborators of the StormSense project in the city of Virginia Beach at vbsensors.bvgov.com. You can access these data directly and see they're highlighted based on when any moderate to minor flood conditions exist in those areas. And so this network exists of data that are incorporated from NOAA's water level sensors. There are 7 of them in Virginia. Additionally, this sensor network also incorporates the Washington, D.C. sensor, technically outside of Virginia, and also Bishop's Head as another NOAA co-ops station that's incorporated within this network of sensors. But strictly speaking, there are 65 within the bounds of Virginia currently, and our goal is that we're currently working to deploy 4 more new water level sensors in 2025 through funding provided by MARACOOS. Now, within these individual organizations, we all, interestingly enough, have different directives in terms of what our goals are, but ultimately, all these individual organizations have focuses on observations for different reasons. And so as a result, the data that we're collecting are being aggregated so that you don't have to go to lots of different websites in order to access this information. The communities that we're working with and partnering with for these efforts do not typically have large offices of people with GIS departments for handling geospatial flooding, or other groups that are specifically focused on emergency management when there's a major flood event that's coming. And so our goal is to aggregate the data quickly where they can find it in one place, but also still access through the links the original data sources for their own analysis. Now, within the StormSense program, as I mentioned earlier, we're ingesting data from a variety of different sensors, and that means the hardware and ultimately the purposes of why those sensors were deployed are inherently different. And so it's important to kind of acknowledge what those differences are. Ultimately, the premier example of monitoring through the National Oceanic and Atmospheric Administration as they're collecting lots of data through full weather stations. At a lot of their locations, they're collecting wind speed, air pressure, all of those things are incorporated into our storm tide predictions because storm surge is driven by winds and atmospheric pressure. On top of that, we're also using the water level data from these sites to help us inform our model's accuracy. And those sensors are using high resolution Ka band radar. So it's a non-contact water level sensing technology, kind of a near field remote sensing approach. Most of these radars are within 50 feet of the water surface, and they simply emit pulses of microwave radiation at the water surface, and they can measure this up to 1 millimeter accuracy. Now, the cost for these water level sensors are usually between $35,000 to $50,000, but they get extremely accurate results as they are calibrated in laboratory settings and then tested again in the field. Next is the U.S. Geological Survey. They, of course, also have an observation-based focus as their programmatic directive as a federal agency. And a lot of their work also provides not just boundary conditions from our hydrodynamic models in the context of flux boundaries at the fall lines of the major estuaries of Virginia, but we also use the data from their Ka band radar sensors, and those are typically accurate to 3 millimeters of accuracy or less. And so they're very high resolution as well. And their sensors cost slightly less at about $26,000 to $30,000. And these are based on last year's US dollars in 2024. So in the context of inflation, they're slightly higher than that now, but they do an excellent job of monitoring those things. And so ingested into StormSense now, of course, we have 2 different types of sensors that we are using within our communities. There are a couple of different vendors that handle this as well. And so we have been using some ultrasonic sonar and Ka band radar sensors. The sonar sensors are accurate typically within about 2 to 3 centimeters, depending on whether or not you have a storm surge event taking place or if it's just typical tidal conditions. The radar sensors are, as we field tested them, accurate to about 2 millimeters in accuracy relative to the root mean squared error method of measurement. We've tested this by co-locating sensors next to NOAA and USGS sensors in the past in these communities to ensure that the relatively lower cost of these sensors is low cost, low energy water level sensors are not acting at the detriment of accuracy from a scientific perspective. On the other side of things, we also have some rapid deployment gauges, as we kind of call them. basically we temporarily will deploy these during major storm events, and they can be bracketed to light posts or other places that are believed to be in the path of inundation. They help us enhance the prediction of our models by temporarily deploying water level sensors. And then finally, our newest generation of sensors, we're calling this the hardware, the StormSense VIMS, or so named for the Virginia Institute of Marine Science where I work, but it's a video inundation monitoring system, and it has an algorithm on board called Flood Vision AI that essentially is allowing us to incorporate in real time um, water level imagery that's coming in from oblique pictometry collected by these web cameras, and it's translated into water levels using 4K resolution infrared camera that's on board, and then taking that information and translating it into water levels using edge detection and machine learning. So, if you're not familiar with how these different types of near field active remote sensors work, we focused on these primarily because they don't require very much maintenance um, relative to in situ pressure transducers where biofouling is a problem. In this case, usually algal matter will kind of collect around pressure transducers, and that translates to additional maintenance, but also lack of accuracy in terms of water level prediction, since the pressure around those types of transducers is kind of fogged by increasing layers of algal growth on them over time. And so, because of that, all the water level sensors in StormSense are active remote sensing technologies that are leveraging the benefit of not being in the water, but being able to measure the water elevation by non-contact methods. Typically, these sensors, we apply for grants to help defray the sensor costs, then order the sensors and assemble them. Depending on the context, we'll use radar or ultrasonic sonar. The reasons why they're different is because Hampton Roads in Virginia, where we deploy most of these sensors, has a lot of military bases. And there's a lot of interference on each of those different spectra for different reasons when military training or operations are taking place. Next, we then take the water level sensing data and conduct a tide watch over 12 hours to kind of give us the highs and lows of the current tidal fluctuations, then revisit that at 1 month and then every 3 months after that to ensure that the seasonal values are appropriate. Then we translate the data from 4 to 20 milliamp measurements of distances to the water to relative datums to make sure that those data are important and relevant to the individual locations they're being collected. That we then incorporate a spike filter for automatic alerting. This ensures that if some random piece of debris or object below the surface is there, that it's not artificially sending out alerts saying, hey, it's flooding at this sensor, when really there's maybe someone fishing from a boat underneath a bridge that happens to be under the sensor at the time. It doesn't register that 2 to 3 foot increase by hitting the boat deck instead of the free surface of the water as flooding, because then that causes people to not believe that the flood alerts are relevant in the future. We also use high frequency waveform smoothing because sometimes there's instantaneous waves underneath those water level sensors, and we want to be measuring the mean values. So they're also energy conservative. These water level sensors are collecting data every 6 minutes, and they go to sleep for 5 of those 6 minutes, then wake up, collect data over a 60-second period of time, and average those values into a single instantaneous value that's recorded in the cloud before it goes back to sleep for the next 5 minutes until the next 6-minute measurement is recorded. Now, in terms of StormSense's sensor accuracy, when we first started deploying these in 2018 to 2020, there was this initial question of whether or not the relatively cheaper hardware that we were using were at least relatively as accurate as the federal sensors. And because the goals of a lot of these communities are trying to determine whether or not individual sites are in the floodplain and whether they should obtain optional risk insurance, we conducted a study to compare the differences by mounting some of our sensors to the same sensors as the U.S. Geological Survey's sensors in the city of Virginia Beach. Since they had multiple USGS sensors there, we deployed them at 4 different locations on the same bridges, but a good distance apart, just to ensure that there's no interference. In most of these cases, we're using ultrasonic sonar sensors instead of the Ka-band radar, so obviously already they're not in the same frequencies to begin with, so they shouldn't be interfering with each other, but just for the purposes of comparison, we were using some ultrasonic sonar sensors, and the hardware for those sensors were roughly $3,000 at the time we conducted the study in 2018 to 2020. And then we compared the data over a 4-month period of time, comparing them relative to the infrastructure used by the U.S. Geological Survey's sensors. And while our sensors were not as accurate as the ones deployed by the U.S. Geological Survey, we did find that the aggregate root mean squared error among these four sensors from November 2020 to March 2021 was accurate to within plus or minus 1.18 centimeters. And during this period of time, there was a king tide in November and 4 minor nor'easters in January and February that took place. So we had some pretty significant amplitude minor inundation events that took place that allowed us to compare pretty reasonably a mix of regular tidal conditions with extra tidal conditions. Now, next, as I mentioned, we've been deploying new water level sensors. And so, it's often interesting for folks to see some of the challenges that we encounter with this, but also the benefits of partnership. In this instance, last year in spring of 2024, in partnership with the Chickahominy tribe, we deployed a new water level sensor on a dock along the Chickahominy River that feeds out to the James River in South Chesapeake Bay. And this water level sensor is maintained by one of our vendors, Greenstream. It was integrated into the StormSense platform in June 2024. Now, typically the next step with this is that we like to take the water level sensing data that we have and provide 36-hour tidal forecasts in those locations. Through harmonic decomposition of the influence of the sun and moon in these tidal areas, we can provide forecasts up to 36 hours in advance as a kind of rolling window moving forward. So as we were working to integrate these data into the VIMS Tide Watch charts to provide these forecasts relative to the North American vertical datum, it's the geodetic datum that's used for providing land survey information, and for people trying to obtain flood insurance, that gives you your freeboard standards as well. But we also relatively convert these to tidal datums. So if water is your basis, then the mean lower low water datum as well is provided. Now, as we started going through this process, a significant portion of our effort involves survey benchmarking and translating those data to the appropriate vertical datums that we need to use for actionable decision making. So as we deploy the water level sensor, you'll see that basically the sensor box along with the sensor itself kind of consists of the solar panel along with the water level sensor, the battery inside that's recharged by the solar panel, and then of course finally the data logger and the antenna that transmit this information first to the cloud using cellular broadband data or satellite, depending on how remote these locations are. And then, of course, as a lot of planning goes into deploying these individual sensors and coordination with community partners that help make this information available. One of the weird anomalies we encountered in 2024 was the convergence of these different cicada swarms that were taking place. And so as we were preparing for hurricane season to start in June of 2024, we had a lot of weird anomalies under our sensors in a couple of the new locations that we were deploying. And one of the worst spots that we saw this was in the Williamsburg area at the site where we deployed a new water level sensor last year, the Chickahominy tribe. And this was simply a convergence of the two major cicada swarms that were taking place at the time. They were large enough insects that were swarming underneath our water level sensor. We had a lot of strange data spikes that were occurring at this location. It was very hard to calibrate the sensor for about 2 months of time at this location. And so thankfully we haven't had that as an issue this year, but it is one of those interesting environmental idiosyncrasies that you run into of one site that may not be so bad at other locations. But anyone who lives in South Chesapeake Bay near the water, a lot of the sound of the droning of the cicadas carries over the water very well. And so our ultrasonic sensor struggled a bit with just the size of the individual insects flying underneath the path of the ultrasonic sensor between it and the water at the dock at this location. But thankfully, it was not an issue with our newest water level sensor at StormSense. We deployed this in June of 2025 along the Pamunkey River in partnership with the Pamunkey tribe on their reservation there in King William County. We're currently working on integrating tidal forecasting at this newest site that was just deployed last month. Now, typically we want at least 30 days of water level sensor data just to provide us at least a mean value that we can incorporate into the model for tidal decomposition. And at that point, then we can start to provide amplitude, phase, and frequency forecasts for this location looking forward. And so that should come online in the next few weeks for this particular location. 3 more water level sensors are planned to be deployed in Virginia's Middle Peninsula region. Or kind of finalizing the site surveys to make those deployments happen, ideally before the fall tidal flooding season. And finally, 6 new water level sensors are planned for deployment next year in Hampton Roads in 2026, and 3 of those sensors are based on some new next generation water observing technologies leveraging AI to make their deterministic identifications of water level. So here's an example of what this looks like. This is a prototype for what ultimately became the video inundation monitoring system. It uses a web camera using 4K resolution night vision and edge detection, as you can see kind of highlighted there with green lines here. This is an example of Hurricane Florence in 2018 when we first started testing this technology with an Amazon Web Services deep lens camera that we had won as part of an award that we had received for StormSense based on our initial efforts in proliferating water level sensors in urban and rural communities in Virginia. It essentially translates those pixels to depths for flood monitoring. And so while we started deploying some of these water level monitoring technologies ourselves, one of the things that we started doing immediately is one of the weak points that we first found when using this technology is that the deep lens camera couldn't see at night. And so we started using water level sensors that were capable of seeing things at night. And in partnership with the U.S. Geological Survey, they have lots of web cameras throughout the continental United States in their platform called HiViz. And so this particular platform has lots of reservoir cameras and stream flow cameras that give us a very quick description of what's happening in those locations, and they're extremely high resolution. They have 4K resolution, but they also, most importantly, have infrared night vision, so you can see water levels 24 hours a day. And so we've been training a machine learning model along with an edge detection model to help us identify pixel values to extract free surface elevations of the water for stage determination. And of course, the natural strengths of these types of models is that you can see what's happening in the field of view of these cameras. And emergency managers love this because they can very quickly see that indeed there's flooding that's happening when they see critical thresholds being reached by these types of cameras. It will draw their attention to them, and they'll be able to view and see whether or not indeed flooding is happening within the field of view of the camera, or if it's some random obstruction that's in the way of the camera. So as I mentioned, some of the weaknesses that are involved with this is, of course, you've got to be able to see. So fog and heavy rain can be problematic for these types of sensors, which are not weaknesses of radar sensors. And so kind of a mix of the different technologies really help us get a very good idea of what's happening on the ground at locations that are subject to inundation. Also, of course, because it's a camera, it's more energy efficient because it's not emitting pulses of radar or ultrasonic sonar, so it doesn't require as much energy to operate. But on the negative side of things, it is a little bit more difficult to determine things that are happening due to light attenuation from dawn and dusk, when the sun or moon might be in view of the camera directly within its field of view, or the reflection of the sun and moon are visible on the surface of the water if it's very still. This also can be problematic as the natural balancing and focus of the camera are a little bit more challenging when there are extremely bright objects in view. And so, as you might would imagine, we've been translating these free surface water elevations predicted by a machine learning model in collaboration with this new research that we've been conducting with the U.S. Geological Survey for the last couple years. And so we have a machine learning modeled water elevation in blue. And so in some instances, you can see the model struggles to figure out whether or not the reflection of the water is the free surface elevation, or if it's something else, if the water is extremely still. And so relatively to mild turbulent waters do a pretty good job of predicting typical tides, but also if there's a lot of fog in view of the camera. That's another thing the sensor struggles with. If it can't see its target field of view, that's also challenging because it now can't see where the water is to determine whether or not the elevation is at a particular spot or not within its frame of reference. Now, overall, our root mean squared error with this type of model, just showing an example of some of the data we recently published in the Journal of Applied Ocean Research last month. The root mean squared error for some of our initial tests with this in January of 2022 was plus or minus about 3.25 centimeters, which we were pretty excited with for a camera that's within about 50 feet of view. In this instance, we've got a web camera about 20 feet from the target area, but of course this is proportional to distance, as a camera's pixel size and density differs depending on how close it is to the object of interest within its field of view. And so, getting into the science a little bit, our final machine learning model that we validated in January of 2022, basically it's collecting images every 6 minutes. This translates to almost 7,200 images collected over the month of January. And for that 720-hour period of time, the mean absolute error was plus or minus about 0.71 inches. And that was pretty exciting for us because about 80% of those predictions were accurate to within 0.05 feet or within roughly 0.6 inches. Whereas another 17% of them that were slightly less accurate were accurate still within about 3.6 inches, and only a few of them were wildly outside of the range we were hoping for and greater than 1 foot from the actual observed water level. And as I mentioned earlier, that was mostly atmospheric conditions that were not conducive for monitoring. So we've been working to incorporate flags associated with those particular machine learning outputs to indicate that the model's not very certain in these instances of what's happening. And now it's getting to the point through object recognition where it's starting to identify whether the conditions are fog or rainfall and whether it's nighttime versus daytime fog, and those types of things that help us identify the specific conditions where the deviations were greater than 1 foot. And this is based on training data that were posted on ScienceBase from Paul Renaud and Keegan Johnson in 2024 from the U.S. Geological Survey, and we were able to recently publish these results in an article in Applied Ocean Research in June of 2025. Now that we've got water observing data from a variety of different types of sensors, we have automated alerts connected to many of these types of water level sensors. We coordinate this effort with the National Weather Service, along with other local offices of emergency managers, just to ensure that we're not putting out differing information from what the advisement of those individual groups and organizations are. The city of Newport News specifically has taken data from their water level sensors. And in fact, they recently had all of their sensors updated by Greenstream in the last couple of months with the latest technology. And essentially, they established critical flood alerts at different locations. This is an example of a non-tidal water level sensor, but a large amount of rainfall that took place a couple of years ago in August. At the end of July, triggered this alert that eventually sent out information so the communities will use this information to help validate the conditions on the roadways and in different places where the transportation infrastructure or actual infrastructural assets are adversely affected by flood damage. And this information is also useful from the context of providing automated alerts. This is helpful mostly because it not just only provides additional credits through the National Flood Insurance Program's community rating system maintained by FEMA, but there's also the benefit of these water level sensors providing actionable information to people that are subscribed to these locations. And so this kind of provided some tangible cost savings for people in special flood hazard areas in these cities. But on top of that, the automated alerts help people decide which directions they might want to travel on their commute home from work if they're subscribed to these locations within Newport News. Now, of course, if you're curious about where you can find these forecasts produced by the Virginia Institute of Marine Science, this portal is maintained by the Center for Coastal Resources Management where I work. And so you've heard me talk about the TideWatch model. The TideWatch charts provide time series forecasts. And so all the locations that we're incorporating observation data through StormSense, we've been feeding tidal forecasts to those areas, this dashed line representing the next 36 hours looking forward. Just to provide you an example of what this looks like. This is an example of the Newport News number 3 sensor, just kind of showcasing what this looks like. But we use those forecasts to help validate the forecasts that are provided by the TideWatch map, which is a geospatial forecast system. That gives us an idea of the timing and the extent, along with the depth of those locations and the observations collected by NOAA's sensors, along with the USGS sensors and the community-owned sensors through StormSense, in coastal Virginia are all kind of conglomerated together. And the purpose behind this is that these real-time observations are leading to very quick response and letting us know whether or not our forecasts are accurate in near real time. And this is another particularly useful resource in the arsenal of flood prediction because it tells us very quickly whether or not the model is approaching convergent flood results and lets us know in real time whether or not those predictions are valid. Now, the way that this model works is this is the Tidewatch map. It collects essentially 2.5 gigabytes of atmospheric forecast data. These are weather driven forcings for a model. So they're driven by pressure and wind speeds for storm tide. And of course, tidal predictions, the boundary of our model, and it updates every 12 hours to provide this 36-hour forecast. Now, its spatial resolution is 1 meter or 3-foot spatial resolution at its highest resolution locations, but in more rural parts of the state, this is closer to about 5-meter resolution, and this is relative to the accuracy of the LiDAR-derived digital elevation data we have available at different parts of the Commonwealth. Now, the Tidewatch map is updating at noon and midnight, so every 12 hours, as I mentioned, it's taking the latest data available from the National Weather Service, and they're using the NamNest data from the latest updates. They update this information every 3 hours, but we run our model every 6 hours to provide these updates in 12-hour intervals at noon and midnight. Now, in real time, it takes about an hour and a half for this hydrodynamic model to provide a 36-hour forecast, leveraging 72 CPUs from our high-performance computing platform at William & Mary for the Virginia Institute of Marine Science to provide these resources to help people visualize tomorrow's flooding today using the SCISM hydrodynamic model. Now, this open source hydrodynamic model is already capable of providing rainfall forecasts, but the digital mapping platform, the bottleneck of the pipeline of providing these updates and incorporating rainfall, when there's a lot more water for the model to keep track of, it takes a variable length of time for it to provide this processing. So we eagerly working on providing a next generation update to Tidewatch's map called version 2.0. And so our goal is actively researching this to incorporate the next generation compound flooding model. And so right now this model exists as a storm tide prediction tool, but our goal is ultimately to incorporate rainfall in the near future. So if you're not familiar with how we validate these models, obviously we use sensors as our primary tool, and the purpose behind that is that they're automated. But you can't always just put sensors everywhere because they require maintenance. And of course, the more remote these locations are, the more important the sensors sometimes end up being, and they're much more likely to go offline for a variety of different reasons, as I've covered previously, to cicadas or other strange events that might be happening at the time that record anomalous data. And so additional information to help validate those models is warranted. And so our goal with this is that community science efforts through a program that I help manage along with Wetlands Watch as a nonprofit partner for this effort in the city of Norfolk. They developed a mobile app called Sea Level Rise. And so we've been using that publicly since 2014, but this effort's been coordinated by media groups since 2017, which has involved a large-scale collection of data every year. And we've collected over 250,000 GPS-reported high water marks to help us validate the spatial extent of flooding by our Tidewatch map. Now, the beauty behind this is not only does it help us validate the hydrodynamic models and flood forecasts that we're making, these 36-hour forecasts in near real time, but then on top of that, they're also becoming in their own right, their own observation-driven GPS data forecasts of their own. As we're mapping the highest astronomical tide of the year, we've been doing this for over a decade now, since 2014 when the map exited its beta. But in this case, the Sea Level Rise app and the large amount of data that they've had available have started creating essentially their own interpolated rasters of the maximum flood extent of the king tide each year. And so over the last decade, we've been able to collect that information and help us provide some context to sea level rise predictions, not just in terms of predictions, but this is an observation-driven model. So we're spatially tracking inundation to help produce new types of models to verify the extents that are being produced in sea level rise forecasts. Now, just to give an example, this year in 2024, we collected 22,845 high water marks from 187 individuals that collected data over a weekend that the king tides took place from October 17th to the 20th in 2024. And not only during the highest astronomical tide of the year is this event happening, we have some very avid volunteers that are willing to help us collect data at a variety of different um, extra tidal flooding events that will take place throughout the year. For example, in March of 2024, we had a high water event on the weekend of March 24th through 26th. And also the highest astronomical tides of September were mapped as a training in preparation for the October highest astronomical tide of the year last year. And so we train volunteers to help us collect these data, but as it pertains to the sensors that I've been covering in this presentation, this provides additional context for communities to say, hey, we have confirmed information that there was in fact flooding here during the highest astronomical tide of last year, and that inundation in the future is likely to happen here. So we coordinate this information with local communities in both rural and urban localities, and we use this to help guide where new water level sensors should be deployed. We have confirmed flooding on the ground in these places to ensure that not only would it be useful in these locations, but that it's likely to become more useful as inundation increases in the context of predicted sea level rise in the future. Now, if you're not familiar with Catch the King, we share data related to NOAA's water level sensors and tidal predictions from VIMS's Tide Watch service at a variety of different locations throughout the tidal region of Virginia, along with North Carolina and parts of Maryland. And in the inaugural year of Catch the King in 2017, we won the Guinness World Record for being the world's largest environmental survey when we collected 59,718 high water marks in a period of less than 6 hours during a single tidal peak in 2017. And so with all the data that we've been able to collect from this year, we'll be doing this mapping effort again. Again, it helps us identify new locations, deploy water level sensors, but also validate hydrologic predictions like the hydrodynamic model Schism driving the TideWatch map, but also anyone else can actively access the data after these events to help validate their own decision making for their communities. This year's Catch the King event is taking place on the 10th through the 12th of October in 2025, essentially throughout the entire Atlantic coast of the United States. That's when the highest astronomical tide of the year is predicted to be. Now, if you're not sure what these types of things look like in practice, this is the 2017 example of Catch the King, where we have lots of individual dots populating a map on beaches and in estuarine environments all throughout coastal Virginia. So you can see the histogram there in the top left corner where all the individual points are being collected and the frequency at which that's taking place, but then some little inset maps highlighted there along the mouth of the Lynnhaven River in Virginia Beach, or this example of Norfolk's famous Hague region that mimics the relative uncertainty of tidal fluctuations you'll see relative to the Hague in the Netherlands, for which it's named after. And in this instance, there's a lot of inundation that takes place in these different areas, and so our king tide mappers have helped us map these in past events. We then translate these points as GPS breadcrumbs into a contour map that we can use to geospatially validate the accuracy of our flood forecasts. And so with that, we kind of compare those cell center points, and that gives us an idea of how the inundation is performing relative to what was predicted up to 36 hours in advance. And so that gives us a metric that's essentially just based on a distance formula between the points and the cell center points of what we call a mean horizontal distance deviation between what the model predicted and what was actually observed. And so here's some examples of what our volunteers have used in the past when they look at the TideWatch map shown there on the right in anticipation of inundation, where there's flooding near Hampton Boulevard, near Old Dominion University, and the city of Norfolk, Virginia, compared to points that are collected by the former executive director of Wetlands Watch, Skip Stiles, where he had showcased what the app is capable of doing on mapping out the contours of where the inundation is happening. This also gives us a nice opportunity to kind of describe what those differences look like between mapping on public property and, of course, weird, things that will happen where obviously our models predicted some areas that people can't walk onto private property through backyards to map. But this is still better than nothing in terms of translating that to an elevation. We can then identify that we don't need people to trespass on private property. All these points are being translated to a digital elevation model. If all of these points are confirming that the water elevation was indeed 3.825 feet above mean lower low water, it's probably safe to assume that a lot of places that were that same elevation within a half a mile of that location also flooded at that same elevation. And so, yes, while you might notice that there are some spots that our model may seem to have overpredicted, it turns out that water was in those backyards, just that our volunteers can't go in those places. And so we always advise them to be safe as they're helping collect data to verify the accuracy of these models while still using data-driven assumptions based on that information to help us cover the areas that they can't effectively map or that we can't get drones or satellite imagery of during those time periods. And so our next steps using this information is that I've covered how our StormSense platform works in Tidewater, Virginia. It's ingesting data from the federal government's sensors through the National Oceanic and Atmospheric Administration, along with the U.S. Geological Survey. We have 17 of those sensors total that we've been ingesting in collaboration with them. And their open API links that are shared through their websites. We're also coordinating with the state in Virginia. The Virginia Department of Emergency Management recently replaced what was called their iFlows system with some new water level sensing apparatuses. Most of them are active remote sensors that have been deployed by Greenstream, and so we're working to integrate the public API links with coordination through the Virginia Department of Emergency Management to add those to StormSense for their new deployments that have happened in the last 12 months. And then StormSense has 48 water level sensors currently, but 20 new water level sensors have been funded through MARACOOS to be deployed over the next 5 years. The first of which, as I already covered in this presentation, was deployed in the Pamunkey River last month, and 3 more are still planned by the end of the year in the Middle Peninsula region of Virginia in coordination with localities there. And then, of course, next year we plan to deploy more water level sensors in Hampton Roads. 3 of those water level sensors are currently planned and slated to be machine learning AI water level camera sensors. And 3 of those will be radar water level sensors that are located safely outside of the regions where military installations are deployed in Hampton Roads. And so, in review, we covered a lot of things. There's been a lot of words said and a lot of words on the slides. Sometimes pictorially, it's helpful to represent. We covered StormSense. We have these key performance indicators to let us know in the communities whether or not this information is actionable. A lot of the communities, like the city of Norfolk, for example, have used this to kind of guide rain barrel deployment to collect runoff from roof lines and translate that into geographic information systems for collaborative sharing and a unified kind of visualization platform to let people know, well, what do these floods look like in my community? And so with the data that is provided by the Tidewatch map and the verifications through community science efforts like Catch the King, it helps us identify where inundation is happening frequently and how those might impact transportation infrastructure in the future. And so with that, we're getting a better idea of where inundation is happening in different places. And we're sharing the data from Catch the King along with our model publicly so that planning district commissions like the Hampton Roads Planning District Commission has recently received funding for new roadway flooding sensors. And we're excited to see how we might be able to assist them in that effort as they're already aware by the communities where there's inundation happening in their localities, but the data that are collected by those sensors are also helpful in validating our forecast efforts. And so targeted notifications and other things are things that are currently being considered along with Waze integration to let people know where there's flooded roadways. Because oftentimes when you have flooded roadways, automated route guidance platforms like Google Maps and Waze tend to lead you down streets that don't have any traffic congestion. But oftentimes the caveat of that is that those sensing platforms are not aware that the reason why there's no cars on the road is because it's flooded. And so this is a rude awakening for people that have recently moved to the Hampton Roads region or Norfolk specifically, where there's a lot of military installations. People not familiar with the location frequently have their cars flooded because they're driving through streets that are deceptively deeper than they look in terms of inundation. And we've won some awards recently for this. We won the Governor's Technology Award in Virginia, or the Commonwealth Technology Award for Flood Vision AI in 2023 for our next generation water observing efforts in collaboration with the U.S. Geological Survey, along with International Data Corp's Smart Cities North America Award won by the City of Virginia Beach for our initial deployments there, and a Smart 20 Award for the in the water category related to the Smart Cities Connect effort. Thank you very much for your time and following along with this presentation, and for MARACOOS for helping us deploy 20 new water level sensors in coastal Virginia through 2029, along with many of our community and federal partners that have helped make this observation effort possible.